Chapter 6, Module 5. In this module, we shall discuss how we can compute the fundamental groups of several other surfaces. Previously, we have seen various techniques or various results in connection with fundamental groups of topological spaces in general. We shall utilize them to get the fundamental groups of cylinder, Möbius band and annulus in this module. Before we proceed, let us recapitulate certain facts. If X is a contractible space, then its fundamental group is trivial. If A is a deformation retract of a path connected space X, then the fundamental group of X is isomorphic to the fundamental group of the deformation retract A. The fundamental group of circle is the group of integers. The fundamental group of torus is the direct sum Z, direct sum Z. With this previous knowledge, we try to get the fundamental group of a cylinder, and we see that the fundamental group of a cylinder is the infinite cyclic group Z. A cylinder is a surface homeomorphic to a subspace of R3, that is three-dimensional Euclidean space given by the collection of all points x, y, z such that x square plus y square is equal to 1 and z lies between some minus k to plus k. Here k stands for some real number. Now consider C is equal to the collection of all points of the form x, y, 0 such that x square plus y square equal to 1. Of course, this C is homeomorphic to the unit circle S1. Also, if we put z equal to 0 in the expression of the collection of all points in Y, then we see that C is a subcollection of Y. We shall show that C is a deformation retract of Y. Now we define a retract F from Y to C given by F of x, y, z equal to x, y, 0, and we define a map capital H from y cross I to y given by H of x, y, z, that triplet, comma t is equal to the triplet x, y, 1 minus t times z. Then this H is definitely a continuous function. If we put t equal to 0 in the expression of H, then H x, y, z 0 is equal to x, y, z, and that can be written as the identity function operated on the point x, y, z. Similarly, if we put t equal to 1, then h x, y, z, comma 1 comes out to be equal to x, y, 0, which is equal to I composed f of x, y, z, where I stands for the inclusion map from C to Y. Also, h x, y, 0 t is equal to x, y, 0 for all t belonging to capital I. So, H satisfies all the conditions for homotopy, and it is a homotopy between the identity function Iy and the composition I composed F. And it is not only a homotopy, it is a homotopy relative to C. So, by the definition of deformation retract, C becomes a deformation retract of capital Y. Now, since C is a deformation retract of capital Y, as pointed out earlier, the fundamental group of C is isomorphic to the fundamental group of Y. But once again, C is homeomorphic to the unit circle S1. So, the fundamental group of C is actually the same as the fundamental group of S1, and that is Z. The next example shows that Möbius band has fundamental group as the infinite cyclic group Z. So, consider the Möbius band capital M, which is the set of all points x, y, where x varies from 0 to some real number a, and y varies between -1 and +1. With the identification that 0y, the point 0y is identified with the point a minus y. This Möbius band contains a circle C as the collection of all points x, 0 such that x lies between 0 and a. Clearly, C is homeomorphic to the unit circle S1. Now, we shall show that C is a deformation retract of the Möbius band M. For that, we define a retract F from M to C by fxy equal to x, 0 that preserves the gluing, and we define capital H from M cross I to M by hxyt equal to x, 1 minus ty. Then of course, capital H is continuous. hxy0 equal to xy, which is the identity function operated on xy, and hxy1 equal to x, 0, which is inclusion composed F evaluated at the point xy, where small I stands for the inclusion map. hx0t is x0 for all t belonging to capital I. Therefore, H becomes a homotopy between the identity map Im and the function I composed F relative to C, which also preserves the gluing. That is, C is a deformation retract of capital M. Therefore, pi 1 M is again isomorphic to Z. Now, this example shows that the fundamental group of the punctured plane, that is R2 minus 0, is again the set of integers Z, rather the group of integers Z, we have seen that the deformation retract of R2 minus 0 is S1. So, the fundamental group of R2 minus 0 should be the fundamental group of S1, and therefore it is Z. Now, one thing can be noted, that if we start with an annulus, then annulus also has the same deformation retract S1. Though annulus and R2 minus 0, that is punctured plane, are not homeomorphic, their fundamental groups are same, that is the group of integers. Now the question is, what is the fundamental group of a doubly punctured plane? We have seen that a deformation retract of the doubly punctured plane is a figure 8 space. So, the question boils down to finding out the fundamental group of figure 8 space. So, we need to know the fundamental group of figure 8 space, which is again the one point union of two circles, that is S1 V S1. Now, we note that once we get to know the fundamental group of figure 8 space, we may conclude that the fundamental group of theta space is equal to that of a figure 8 space. Why so? Because theta space is another retract of, rather deformation retract of, the doubly punctured plane. Now, we intend to compute the fundamental group of figure 8 space and thereby get the fundamental group of doubly punctured plane, as also the fundamental group of theta space. For that matter, we introduce, rather state, the very well known theorem which we call Van Kampen's theorem here. Now, let us state Van Kampen's theorem. Suppose X is a topological space and U V are two open sets in X such that X can be expressed as union of U and V. Also suppose that we take a point x0 from the intersection of U and V. U intersection V should be path connected. In this setup, if I and j are the inclusion maps from U to X and V to X respectively, and these inclusion maps induces homomorphisms I sharp and j sharp between the corresponding fundamental groups based at the selected point x0, then the theorem says that there is a surjective homomorphism phi from pi 1 ux0 star pi 1 vx0 to pi 1 xx0 such that phi restricted to pi 1 ux0 is I sharp and phi restricted to pi 1 vx0 is equal to j sharp. In particular, if U intersection V is simply connected, then pi 1 x is isomorphic to the free product pi 1 u star pi 1 v. Now we use this theorem to show that fundamental group of Sn is trivial whenever we take n greater than equal to 2. Now since Sn is path connected, its fundamental group does not depend on the base point. Now we choose two particular points. One is a point P which has coordinates all zeros and the last component is 1, and the other point Q which has all the first n component 0 and the last component as -1. Now we consider u as Sn minus the point P and V as Sn minus the point Q. Now since P is a singleton, it is a closed set in Rn plus 1 and therefore U is open. Similarly, V is also open subset of Sn. Now again, Sn is U union V, and if we take U intersection V, then it contains all the points of Sn except for 2 points P and Q. So, U intersection V is path connected. Now we choose any point x0 from U intersection V. By using Van Kampen's theorem, there must exist a surjective homomorphism from pi 1 u x0 free product pi 1 v x0 onto pi 1 Sn x0. Now, each u and v being homeomorphic to Rn for n greater than equal to 2, these two u and v, these two spaces are contractible. And we know that contractible space has fundamental group trivial. So, pi 1 u x0 is trivial and pi 1 v x0 is also trivial. Consequently, their free product is a trivial group, and so fundamental group of x best at x0 is trivial. The figure 8 space is a one-point union of two circles, that is S1 union S1. We claim that fundamental group of figure 8 space is the free product Z star Z. So, we consider the open sets U and V as described in this figure. The first one, a circle with a portion of a circle, this is the set U. The second one, that is the circle on the right and a portion of the circle on the left, stands for the open set V. Then if we take their intersection, then that gives us a figure like what is appearing in the third position. This U intersection V, as seen in the figure, is a contractible space. and hence has a trivial fundamental group. So, fundamental group of X is isomorphic to the free product fundamental group of U star fundamental group of V, which is isomorphic to fundamental group of S1 star fundamental group of S1, and that is isomorphic to Z star Z. So, the fundamental group of X, where X is actually the figure 8 space, that is S1 1 point union S1, is a free group on two generators. Applying a similar argument, the wedge of n circles have fundamental group Z star Z star Z. There should be n components. That is a free product of n many infinite cyclic groups. Hence, it is a free group on n generators. So, what do we mean by wedge of n circles is that n many circles are joined at a single point. There are several surfaces which are non-contractible, neither can be viewed as product of certain topological spaces, nor is a deformation retract of a topological space. For example, if we take real projective plane, how do we get or how do we determine the fundamental group of such spaces? In subsequent modules, we shall develop techniques to get or to construct the fundamental groups of several other surfaces.